Okay, just a minute. I'll share my screen. So is my screen visible to everyone?
Yes, sir.
Yes, sir.
Yes, sir.
Okay, very good, very good. So very good evening to one and all. So I am Jashuran, and I'll be taking some GATE classes on material science. So last week we were discussing about the fundamentals of metallic and semiconductor materials. So shall we see a very brief summary of the previous class? Does anybody remember what was taught in the previous class? How many of you attended last week's class? Can you just raise your hands? Okay, I hear 3, 5. Okay, so a significant number has joined. Can you just tell me like what was discussed in previous class?
Hello.
Yes, you're audible. You can tell me.
Types of bonds and its properties.
So we discussed the sorry, just a sec. Types of bonds, right?
एटॉमिक अरेंजमेंट और सर जो ब्रेवेस के लेटर्स जो थे
So atomic arrangements, okay.
और मैक्सिमम थियोरेटिकल पैकिंग एफिशिएंसी जो था सर वो भी
Yes, packing efficiency. So don't worry, we will discuss that again. We discussed regarding atomic arrangements, packing efficiency, then
Types
the
of
types of
bond.
bonding. So anything else we discussed other than
Then
this?
atomic spacing.
Yes, interatomic spacing.
Difference between metals and non-metals.
Okay, the differences, right? We discussed. That is physical and chemical properties, right?
Yes, sir.
So, okay, so these are some of the things we discussed. Other than this, we also discussed the various parameters we require for choosing materials. Okay, like what should we check before we choose a particular material for use in a particular application? That also we discussed. And also we saw about the various atomic arrangements, then the packing efficiency for that is in a two-dimensional space. Then we discussed the type of bonds. So under the type of bonds, do you remember what all we discussed?
Ionic, covalent, metallic bond.
Yes, covalent. Just a minute. Then we discussed ionic and then metallic. So these are the three major bonds we discussed. Other than this, there is one more bond. That is,
Secondary bond.
yeah, sorry, just a sec. Secondary. So these are the things that we discussed, okay? So that's what is written here. I thought I could go, oh yes, we also forgot about CT. What is CT? Do you know what CT is? So
Coefficient of thermal expansion.
yes, coefficient of thermal expansion. So these are the things that we discussed last week. So I thought I could go deeply into semiconductor materials, but as of now, let's not do that. Anyhow, you guys will be having more classes in the coming days. So once I have covered about the metallurgy part, then we can go into semiconductors. Okay. So this is the content of today's class. I do not know how much we will be able to cover in today because the topic is very vast, right from the crystal structures and stacking sequence all the way down to crystal imperfections. So my guess is we would most probably cover these two today. Others, I don't know whether we can do it. Yes, crystallographic directions also we can do, but these two, I think we may have to go for next class. So I'll talk to the coordinator regarding this and try to get a slot some other day, like Wednesday, so that there is no interruption. No, I don't have to finish by 1 hour itself. Yes.
Sir, on Friday we are free. Sorry, Wednesday में सब free हैं.
Yeah, yeah. That's what I want to do. I want to ask Wednesday slots. So yeah.
Yes, sir.
Yes, yes.
Our recommendation also that, sir.
Sure, sure. Yeah, I'll ask sir for Wednesday. If not Wednesday, then Sunday. In any day, I'll ask, because 1 hour seems to be very short, and I seem to have rushed it. So yeah, I'll do that. So we'll try to cover these three today. So again, this is just a rough summary of the previous class we've already seen. So if you want, you can take a screenshot of this particular thing, because if anyone is willing to do any research in material science, this data here can be very, very helpful. So especially, if you are asking about sodium chloride and silicon, carbon, and also iron and aluminum. So in GATE, you may be, like sometimes asked questions from these materials, and it is better to keep the bonding energy in mind. So sometimes, most of the time, the data will be given, but worst case scenario, if they don't give, we may have to remember. So if you want, people want, they can take a screenshot of this. So coming back to metal crystal structures, okay. Last week, yes, I made a mistake. So I thought, this HCP could be solved the same way as we solve this, cubic structure, square. But we'll look into how we do it. And you guys were right. This HCP packing has more efficiency compared to that of a square plane. So we'll look at it, okay. So again, the maximum theoretical packing of 2D system we saw in the previous class. So for those of you who didn't come, I'll just give a brief explanation. So we know that the packing factor here is the area occupied by the atom to the area occupied by the whole unit cell. Our case, it's a 3D, a 2D image. So what is the area occupied by the atom? So it is nothing but, the number of atoms that are there in a particular unit cell, then the area of the atom, and then the area of the whole unit cell. In our case, what do we have? We have an atom which is in contact with 4 other atoms, like 1, 2, and then likewise it will be contact with another atom here and here. So it is shared, the unit cell, the atom in the, at the corner is shared by 4 atoms. So that is why we have 4 into 1 by 4, right? And then, as we know, the area of the circle is pi r square by 4. Okay, pi is square by 4. Then the whole area of the unit cell is a square. That is the area of the square. Okay, so this is the area of the circle, the area of the square. Atoms we consider as a rigid circle in this case, in a 2D case, and in a 3D case, we consider that as a rigid sphere. Okay. So when we finally solve this particular values, we get the theoretical packing factor as 78%. So next,
So,
yeah, yes.
what is 1 by 4?
Just a minute. 1 by 4, right? So
Yes.
in a unit cell, okay, we have Okay, this is, consider this as your unit cell. Just a sec. We have a unit cell over here. This is a 2D unit cell, and we have 4 atoms, right? So if we see only 1/4 of this particular atom is staying within the unit cell, is it not?
Yes, sir.
So only 1/4 is there, right? That is why we have 4 1/4 atoms. You get it, right?
Yes, sir.
Okay, so the rest of it is outside this unit cell. So we want, what is this area occupied by the atom? Actually, it's by the atom in the unit cell. Okay.
And sir,
Yeah.
the area occupied by unit cell means a unit cell is the group of four atoms, right?
Yeah, actually what we are doing is, this unit cell is actually an imaginary term. Okay. So we are, based on the pattern that is available for us, we are creating these unit cells. Yeah, we can assume here that a group of 4 atoms constitutes a unit cell, but not 4 atoms entirely. So, the unit cell is like a geometric structure, right? So,
Okay.
we just, when we draw a geometric structure in this particular group of 4 atoms, the entire atom is not covered. So we are taking the center points, okay, of the atoms for, um, ease of calculation purposes. So that is why when we take the center points, right, we like, what can we say? We can find out, like, the radius of this particular circle. Okay, so this will be 1 r here, this will be another r here. So when we are talking about the interatomic distance, right, that is A, or lattice parameter, it will, sorry, it's not writing. Lattice parameter, it will be equal to the radius of the 2 atoms. So that's why we are like considering like this. And when we consider a unit cell like this, the whole atom is not covered within the unit cell. Only a small part of it is covered. That is 1/4. So that's why, we have taken it like this. There are 4 atoms here, and all those 4 atoms, and sorry, only 1/4 of each atom is available within the unit cell. Uh, did I answer your doubt?
Yes, sir.
Okay. So, does anybody else have any doubt in this? Okay, I'll proceed to the next one. So in case there are any doubts, please do let me know. I'll do my best to clear it. Even if there is some confusion also, I will clear it in the subsequent class. So likewise, in the previous class, we had some confusion regarding the theoretical packing of this hexagonal 2D system. And actually, in our the person who last time he told it was correct only. It is actually 91%. Last time we only brought it to 21, or very very low number. So please don't follow
22
that. Yes.
लास्ट टाइम आपने 22 बताया था
Ah,
सर.
yeah, yeah. So that's wrong actually. So the correct answer is 91. So this is the highest again for HCP in a 2D system. The HCP's packing factor is the highest. So we'll just see how this particular problem is solved. So what we will do is, we will consider the hexagon, right? The arrangement is hexagonal here, no? In this hexagon, we will take a small triangle, right? And this consists of 6 triangles, right? 1, 2, 3, 4, 5, and 6, right? So 6 into area of AOB. So these are all triangles spaced in equal length, is it not? Wait, I'll draw it. So we have one triangle here, 1, 2, 3, 4 triangles, right? So they are all spaced. Sorry, 1, 2, 3, 4, 5, and 6. 6 triangles equally spaced. So all we need to do is find the area of one particular triangle, and we will be able to find the area of the entire hexagon. So to find the area of the triangle, we have this particular formula, root 3 by 4 a square. Okay. So we already know that the value of a, okay, we consider each of this as a, each side of the hexagon as a. So we also have discussed that the a is nothing but the interatomic distance, is it not? So just a minute. Yeah, the a is the interatomic distance. So interatomic distance also means two radius, is it not? So radius 1 and radius 2, 2 into r. So that's why instead of a we have 2r over here, 2r square. And then what will happen when we square this? We get root 3 by 4, this becomes 4r square. So 4 and 4 gets cancelled, and remaining you have root 3r square. Okay. So this we substitute over here, and this is the area of the hexagon, 6 into root 3r square. Next we come to the packing factor. So in the packing factor, again we will look at the number of atoms in that particular unit cell, right, times the area of the circle. So in previous case I used it in terms of the lattice parameter a. Here I have directly substituted the radius value. So we already know, because see here it's pi a square by 4. Here instead of a we put the 2r. Let's just see here, pi, instead of a we put 2r, pi a square by 4 na. So it is pi into 4r square by 4, 4 gets cancelled, remaining you have only pi r square, right? And that is what is kept over here. Just a sec. Okay. So this is the area of the circle over here, and this is the number of atoms in the unit cell, and this is the area of the unit cell. What is the area of our unit cell? Our unit cell is a hexagon, right? And the area of the hexagon, as we found out, is over here. So we substituted all this, and when we solve we will get 0.91. That is the 3 and the 6 gets cancelled here, we get 2. So 2 plus 1 is, we get 3. 3 into pi, the r square and r square gets cancelled, and then we have 3 over here, right? So 3, 2, okay. 3 and the 6 here gets cancelled and becomes 2. So we have pi by 2 root 3. So when you solve this, your answer will be 0.91 or 91%. So is this clear, the theoretical packing factor? So for the 2D system, the maximum, the highest possible theoretical factor can be achieved in the HCP crystal structure. So is this clear, guys? Any questions?
Yes, sir, it's clear.
Okay. I'm sorry about the handwriting, so it's if it's a little messy, please forgive me. So another thing, you guys, I want to tell that from the next class onwards, since I'm unable to cover everything in a very short time, I will share with you all the materials, okay, that I'm going to make. That is right from the YouTube link, the YouTube channel, which will have all the videos, to all the materials I personally refer to for my gate preparation. So I will prepare like a Word document format, and I will share the drive link with you guys so that all of you who attend can access it, and it will be easier for your preparation. So okay, now let us go into the metallic crystal structures. So these are some of the characteristics of metallic crystal structures. Okay, one, they tend to be densely packed. We already saw this, right? And the reason why it is densely packed is because only one type of element is present. So almost all the atomic radii are same, not almost, like all the atomic radii are the same. So there is no directional bonding, as we already saw. No, it is uniformly spread throughout. Everything will be uniformly spread, and there is no competing charges that will cause them to go apart. So the nearest neighbor distance tend to be small in order to lower the bond energy. So we already saw in our previous class, right? If this is the attractive force, attractive energy, this is the repulsive energy, and at this particular point the force of attraction is high and bonding energy is at equilibrium. So beyond this, what will happen? I mean, this is distance. If we bring it too close, the repulsive energy will become too high. If we take it farther and farther away, then the attractive force will automatically go away, right? So for metallic bonding, since they are all the same atoms, they are able to stay close together due to similar charges and electron crowd structure, right? So since metals are very uniform in their arrangement, they have very simple crystal structures, and we shall have a look at them. So is this clear, you guys, about the metallic structures? If it
Yes,
is
sir.
okay, so I mean, this is just theory. We'll not go deep into this. So first, let's look at the simple cubic structure. Okay, so this is how usually a schematic representation of the simple cubic structure will look like. So it is actually quite rare. Very few crystals have this particular structure, like polonium or cesium chloride, or just very few elements will have this sort of a crystal structure. So the coordination number is 6. That is, each atom is closely bonded to 6 other atoms. So this is one. We have one over here, 2, 3, 4, 5. It's 1, 2, 3, 4, 5, and one more at the bottom, 6. So it is closely surrounded by 6. Even in this diagram you can see, no, this is an atom, some atom. It is surrounded by one on top, one here, 4, 5, and 6. Okay, so let's look at the atomic packing factor. We know that the atomic packing factor is, what is the formula? Do you guys know?
Sir, volume of unit cell divided by volume of atoms.
Volume of atoms in the unit cell, actually.
Oh, sir.
Okay, divided by volume of unit cell. So what's the volume of atoms in this unit cell? So
5/4.
number of atoms in the unit cell times, what is this?
Volume of
Like a sphere, sir.
Exactly, volume of the
Sphere.
thermal
sphere. Because we are considering, as I mentioned here, in a 3D structure, it is a rigid sphere, is it not? So the number of atoms in the unit cell, the volume of the rigid sphere divided by the volume of the unit cell. Okay, so how many number of atoms are here in this simple cubic structure? Can we tell?
1.
Exactly. 1. How did we get this number? We have 1, 2, 3, 4 atoms. And then each corner atom, sorry, the unit cell only 1/4 of the atom exists. So 1 into 4 by 4, we just saw that. Okay, so this is the atoms, what can I say, the percentage of atom present in the unit cell, and this is the number of such atoms. Okay, we get 1, and as we know, volume of the sphere is 4 by 3 pi r cubed, right? Divided by volume of the unit cell is a simple cube, that is
A
a
cube,
cube,
A cube.
right? So what will be our final answer if we substitute all this? This A, okay, is nothing but 2r, right? So we will just substitute here. 2r means 2 cubed, 8 r cubed, right? And then 4 by 3 pi r cubed, r cubed, r cubed gets cancelled. Then this comes on top. So finally we get the answer as, I think,
0.52.
0.52, right? So that's what is written here. So the atomic packing factor of a simple cube is 0.52, which is the lowest of all cubic structures. Similarly, we can look at body-centered cubic cell. I think from this particular diagram,
सर
yes,
सर
yeah,
सर मतलब कि जो एक एटम जो कॉर्नर पे है
yes,
उसका तो 1/8 पोर्शन ही एक यूनिट सेल में है, 1/4 थोड़ी है।
yes,
आपने 1/4 लिखा था सर, 1/8 है ना।
wait, one.
आप पीछे
Oh yeah,
कैलकुलेशन
yeah.
लगा।
Sorry. I'm so sorry. I'm so sorry. I assumed it is what do you call that?
2D
This thing 2D diagram. Sorry, this is 3D, right? Yeah. Sorry. This is 1/8 because you're right. 1/8 into 8. Sorry, 1/8 into 8 because this is 3D, no? So you'll have 1, 2, 3, 4, 5. Sorry. This is unit cell. Okay, I think it's a little difficult to draw this actually. So only 1/8 will be there. Sorry, 1/8 will be there. And this unit cell will be shared by 8 other unit cells. So your answer will be 1. But it is not in a, like in a 2D case, because here this is shared by this unit cell, this one, one on top, one on the side, and even in the bottom. So it's a little hard to put it. So it's actually 8 into 1/8. I'm so sorry about that. Next, for body-centered cubic also, the solution is pretty similar. The only difference here is, from this diagram it is pretty obvious, no? You have one atom in the center and then 8 atoms on the sides, right? And the coordination number is very simple, 8, because it's pretty obvious, no? This one atom is in touch with 8. Likewise, even this atom will be in contact with 8 other atoms. So that's how the whole arrangement will look like. And these are some of the elements. So chromium is BCC, then tungsten, then alpha ion, right? Alpha ion is also, alpha phase of ion is also BCC, then tantalum, molybdenum. These all come under BCC structure. Then there are 2 atoms per unit cell. Why 2 atoms? As we had already seen in a simple cubic structure, we have 8 corner atoms into which is shared by 8 other unit cells. So 8 corner into 1/8. So we get 1, right? And there is one atom exclusively in the center just for this particular unit cell. So 1 plus 1 we get 2. So again we'll go for the atomic packing factor. So this is a little slightly complicated. Okay, we'll have a look at this. Sorry. Here what we will do is we will first look at the available data. Okay, we have to find the value of r, right? Because we know that the volume of the sphere is 4 by 3 pi r cubed. Okay, we need to find the value of this particular r. Okay, so what are we going to do? We will take this particular, we'll name this. Okay, we'll call this triangle ABC. Let's call this D and E. I mean, this is just for our reference. Okay, so let's take triangle ABC, right? That is this portion, this particular portion from here to here, right? This particular triangle. Okay, so we know that the sides are A. Okay, so AB is A, BC is also A, and then we know the old Pythagoras theorem, right? So AC square is equal to AB square plus BC square, and AC square is equal to, what is AB square here? That is the side, no? That is A square. Then BC is another A square, the sides. So the AC square is 2A square. Okay. Now we have found, then what about AC? AC is root 2A. Okay. Now we found AC value, right? So this is A, this is C, and this is D. Okay, this diagonal element. Now we are going to look at the diagonal element, right? So what are we going to do? We have now found AC. We have no idea what this is. I'm sorry, this is already written here, but we have no idea what AD is. AD is equal to question mark as of now. Okay, we don't know yet. We have to find. But we already know AC, right? And we also know CD. Okay, so this is also another side, right? So this is also A, no? So we know this. Now we have to find only this diagonal element. So we have AD square is equal to AC square plus AD square, right? And AC square is, we already know, right? Root 2A whole square plus AD square. What is AD square? We have no idea. Sorry, not AD square. This is DC square. DC square is A square, is it not? So root 2 into root 2 is, sorry, root 2 square is, what is root 2 square? Anybody knows?
2A square
Yeah. 2A square plus
plus A
AD
square,
square,
sir.
which is 3A square.
3A square.
This is AD square, right? Now we need to find the value of AD.
AD.
So that's nothing but root 3A, right? So we got this root 3, sorry, which is the eraser here? Yeah, we finally got this root 3A. Now, this whole thing here, right, is how much? We have one radius over here. Here we have a full diameter. So 2 radiuses, right, is equal to the diameter. And then we have one radius over here. So just a minute. I think I'm about to lose power. Please wait. Just give me a minute. Yes. Okay. Right. Yeah. So, um, we have one radius over here, one radius, two radiuses. That is one diameter and one radius over here. So, totally, how much radius we have? We have got. Wait, clear up the space. We have got 4 radius. Is it not? And the 4 radius is equal to root 3a. Is it not? And from this we find the relation of r. R is equal to root 3 by 4a. And once we have found this, uh, we substitute this value straight in the equation. And once we substitute, we get the final atomic packing factor. So does anybody know what the atomic packing factor of BCC is?
0.68, sir.
Exactly.
68, sir.
0.68. It's already here, but yeah, it's 0.68. Next we have FCC. I don't want to like deeply go for the calculation. I'll just roughly explain because time is again very short. So in the face centered cubic cell, we can see that the atoms touch each other along the face diagonals, right? So this is where they touch each other. In BCC case, they were touching along the body diagonal. There was one in the center and it was touching along the body diagonal, but here they are only touching in the face diagonal. Okay, so FCC is a very common crystal structure, and then its coordination number is 11. That is, each atom is touching 12 other atoms. So the coordination number is 12, and the number of atoms in this particular unit cell is a total of 4. Why is it 4? We have 6 atoms in its face, right? 1, 2, 3, 4, 5, and 6. So 6 atoms in the face and 8 corner atoms, right? Shared by 8 unit cells. As usual, any cubic structure, this will be the case, no? So we have 6 atoms in the face and each face atom is shared by 2 unit cell, plus we have 8 corner atoms and each 8 corner atom is shared by 8 unit cells. So our answer will be 3 plus 1, which is 4 atoms, right? Next we have atomic packing factor. Okay, now atomic packing factor is already displayed here. I'll just quickly explain. Like last time, what we are going to do is we are going to use the same old uh, Pythagoras theorem, except here it's going to be a direct answer. Let's consider this A, B, C, and this is a one side. Okay, so okay, for convenience sake I'll draw it here. A, B and C. One side, sorry, A, B is here, no? C over here. Okay, this is one side and B and C is another side, right? So this we already know, R, 2R and R. So this is nothing but 4R. Okay, this is one thing. Another thing is, now we find the value of the hypotenuse with respect to A, right? How do we do that? The simple AC square is equal to AB square plus BC square. BC square is equal to AB square plus AC square. The simple Pythagoras theorem. And AB square is what? A square plus A square. Is it not? A square is A and A. So AB is A square, AC is A square. The answer is 2A square. And BC is equal to root 2A. Okay, this is BC square and this is BC, right? Now we have found the hypotenuse value of root 2A and 4R. Now we can find the R, right? What is it? 4R is equal to root 2A. Therefore, R is equal to root 2 by 4 into A. So we take this and substitute over here. then we get the atomic packing factor of 0.74. So this is the atomic packing factor till FCC. Then there is one more, HCP, we will go for that. Before that, let's have a look at the stacking sequence. So this is, we are only discussing about one unit cell over here. But what if we look at the bigger picture, okay? When we are looking at some image, right, under a microscope, we will be not just looking at one unit cell. One unit cell will be too small to look at. We will be looking at a number of unit cells, a bunch. So they'll all be very small and crowded together. The only way we can tell one structure from another, though it is difficult, the only way is by finding its stacking sequence. So for FCC structure, this is usually how it is stacked. You see, you have the A site, then there is a B site, and then there is a C site. Okay. So one part of the corner atoms come under the A site, the other part of the corner atoms will come under the C site, and some will come under B site. Okay, and then the face atoms will also come under B site, some under B and some under A. So this is the stacking sequence. So this will usually be asked as a 1 mark or match the following question. So FCC stacking sequence means you must say it is ABC ABC stacking sequence, right? Next we have the most important part, that is the HCP. HCP is actually a little complicated when it comes to solving and finding out the atomic packing factor, but we'll still do it. And this is the HCP stacking sequence. Can anyone tell me what it is? Like, we saw that FCC was ABC ABC. This is,
AB, AB.
yeah, it is pretty obvious, right? We have A B A B. Okay. So there will be like the hexagonal pattern on top, and then we will have a trigonal pattern over here. So this is the HCP stacking sequence. Next, we will look at the stacking, like the parameters, okay, the lattice parameter and everything else of this particular HCP structure. Okay, first the lattice parameter is as usual, right? 1, 2, 3, 4, 5, 6, 7. Okay, so this is a hexagon, no? So usually when we are talking about lattice parameters, we only take this A, right? Interatomic distance, that is the lattice parameter, and that is nothing but the usual 2r. So the radius here is A by 2. Next, let's talk about the number of atoms. So actually, let's take a look at the HCP structure again. So if we look at this, right, how many atoms are there? Like, we will consider this whole thing is a unit cell. Okay, this whole thing is a unit cell. So this is a clearer picture over here, right? We have 6 top atoms, is it not? 6 top corner atoms. These are just corner atoms. They will be shared with 6 other common top 6 other unit cells. So we will have 6 top corner atoms shared by 6 other unit cell. Then we have 6 other bottom, right? There are 6 in the bottom, no? So 6 bottom 6 atoms in the bottom, which is shared by another 6 unit cell, plus we have 2 atoms at the faces, right? One over here and one in the bottom. Okay, so they will be shared by 2 unit cells. So that is 2 face 2 atoms at the bases, or we can even say face. Then that is in turn shared by 2 unit cell plus sorry. We have 3 separate exclusive atoms just for this unit cell. So we have the 3 separate units atoms. So what do we have? We have 1 plus 1 plus 1 plus 3. How much? So we have a total of 6 atoms in this particular unit cell. Okay. Next, what else is there? We'll just write down this data separately. So R is equal to, we have A by 2 radius. What else did we find? The number of atoms is equal to 6, no? 6 atoms. Now what we have to do is, we'll just round this off. We have to calculate the C by A ratio. Okay. So I'm sorry guys that I'm going a bit slow, because if we know these fundamentals very well, then the subsequent classes will become easier. That's why I'm going slow as of now. But then we'll work a lot of problems. I'll somehow get the slot changed so that we will have more time and we can solve more problems based on this. Okay. So reason why we are going for this C by A ratio is because here is the first case in all our unit cells that we have a parameter known as height, okay, which is extending up other than the sides. That is why we have a C over here. Okay. And since we have a height, we have to find the relationship between this C and this A. Okay. So for that, we'll just do a rough drawing over here. 1, 2, 3, 4. We'll take the basal plane, basal hexagonal plane, and we have a central atom. On top of this, we will be having 3 atoms. Okay, this is a trigonal structure, and care must be taken to note that this is not C. Okay, this is C by 2, this height, okay, from the basal plane or the top plane to this trigonal structure is C by 2. If we have the top plane, then the trigonal, then another, the bottom plane, this height from the top plane to the bottom hexagonal plane is C. Okay. Whereas this height from the trigonal to the bottom or trigonal to the top basal plane is C by 2. Okay, so here we have taken the height as C by 2. Just a minute. Okay, where is the eraser? Sorry. Yeah. Just a minute. So we have taken the height here as, the height here is C by 2. Now what we will do is, we will draw a triangle like the last time. No, we'll just draw these bisectors, and we get a triangle over here, right? We'll name this, for our convenience, we'll name this A, we'll call this B, we'll call the center point as usual as O. So it's supposed to meet in the center, so the center point is O, and let us take some other point in the top over here as C. Now we have to note that this is not a straight line, rather it is an inclined line, okay, and it is somewhere between the A and O line and A and B lines. It's somewhere in the middle, right? To find that exact value, what we are going to do is, we are going to use some of the oldest geometric tricks in the book. We will use a bisector, a perpendicular bisector. Okay, we draw these perpendicular bisectors. Yeah, sorry. So what we do now is we will name this y. Okay, we have another triangle over here, ABY. Okay, I hope everyone is able to see this triangle ABY. Then at the meeting point of this bisector, right, we will connect what happened? C. Okay, so we have another triangle AC, and we will call this particular point as X. Okay, now is the diagram too messy? Is the diagram clear for everyone?
Yes, sir.
Okay, in case it's messy, just let me know. I'll try to redraw it and explain. So let's take this triangle ABY, okay, which is this thing. Okay, in triangle ABY, yeah, A B Y. Let us this is actually we already saw no in our hexagon. We will divide each of this as triangles, is it not? And each triangle angle is 60. This is an equilateral triangle. Okay, that the total internal angle is 180 degrees, and it can be if we take the angle at each point, it will be like 60, 60 and 60 degrees, right? So what we are doing here is we are bisecting this, are we not? Okay, we are cutting this in the center. So since we are cutting this in the center, this becomes 30 degrees. Okay, so here we have 30 degrees, right? So you guys are able to understand this, right? No problem, no? If there is a problem, please do let me know. Okay, and we also know that this is a side. Okay, so side means what is it? The lattice parameter A. Okay, this also we know, but we have no idea what this is. We have no idea, no clue. Also, oh wait, do we know that? Okay, we have no clue over there, and we have no clue of what. Sorry. By also is. Okay, so what is cos theta? Sorry, cos theta is adjacent by
Sorry. Hypotenuse.
hypotenuse, is it not? Okay, so adjacent by hypotenuse means here what is adjacent? We have the side A, right? So what is the hypotenuse value?
AY.
Okay, and here we know the angle. Okay, cos 30 degrees. What is cos 30 degrees? It is nothing but root 3 by 2, is it not? So okay, there are people coming even now. Okay, so this is AY. We'll just jumble this and we will get the value of AY as something
2a by root 3.
Yeah, 2a by root 3. Wait, cos 30. Is cos 30 root 3 by 2 or 2 by root 3? Root 3 by 2 only, right?
Root 3 by 2, sir.
Yeah, correct. So the AY goes there. So 2a by root 3. This is the AY value. Then we will go for AX. So AX, if we would look at it, it is not exactly at the center. Rather, let's say it is something like 2/3 at a distance of 2/3 from AY. Okay, so 2 by 3 into what is AY over here? It is
2a root
2A root 3. So 4 by 3 root 3 into A. Okay. This is what we get for AX. Then what we will do is we will go for the triangle AXC. Okay, what is AXC? This triangle. Okay, triangle AXC. Now in this triangle AXC, okay, we use this simple Pythagoras theorem, ax square plus x or cx square. Okay, what is ax square again? 4 by 3 root 3 whole square plus cx square is, did you find cx square? Yeah, c
sir.
2 whole square. Okay, so we get 4 4s are 16 by 9 into 3, 27 plus 16 by 4. Okay, it's getting a little complicated. So let's say a value.
Sir, we missing a, sir.
Yes, yes, that's what I was looking for. So there's an a over there, so we'll have a square over here, is it not? So okay, what is this? AC square. Okay, we get 16 a square by 27 plus 16 by 4. Okay, so till this point, is it clear, guys? We got this particular value. Okay, now what we are supposed to do is we are supposed to find the C by A ratio, is it not? So wait, where is the C? I also have a C over here, right? 4 by 2. Instead of C, we substituted this value. Then okay, some sort of confusion. Okay, so the thing is now we are out of time. Okay,
Sir, I want to ask a question, sir.
yes, yes, please tell me.
If मतलब सर एफसीसी में एबीसी एबीसी क्यों कंसीडर कर रहे हैं, मतलब उसका मेरे को वो तो पता है कि एबीसी एबीसी क्यों कंसीडर कर रहे हैं वो डायग्राम देखकर, पर अगर उसको क्यूब के एक फ्लोर को वो माने और बीच वाले जहाँ फेस वाले सेंटर हैं उनको दूसरा माने, फिर ऊपर वाला तो सिमिलर हो गया ए बी सर पैटर्न.
So just a minute, I'll come back. Okay, but before I go back, I'll just tell this thing, since we are out of time, it's already 7 o'clock, so we'll just hold it here, okay? This, remember this, guys. So AC square 16A. We'll solve the rest of the problem because there's some more to solve. Like it will take at least another 10 minutes, I think, 10 to 15 minutes. So I don't want to take the other person's time also. So we'll solve this again next week, okay? And yeah, can you repeat again, bro? This like this FCC, right?
यस सर, यस सर.
Yeah.
सर जो नीचे वाला जो बेस है क्यूब का
Mm-hmm.
उसको ए मान लेते हैं, एंड जो फेस पर है जो स्क्वायर्स हैं
Mm-hmm.
क्यूब वो स्फीयर्स हैं उसको बी मान लेते हैं, तो उसके ऊपर वाला भी तो सर ए ही तो पैटर्न फॉलो कर रहा है.
Okay, okay. So you're saying like how this pattern like exists, right? So
And-
it will
सर
be
मतलब वो तो मेरे को पता है कि वो एग्जिस्ट कैसे कर रहा है एबीसी एबीसी,
Mm-hmm.
पर ए बी भी कर सकता है। मैं ये पूछना चाह रहा था सर।
I'm sorry. Can you ask in English if it's okay? I'm sorry again. So, as far as I,
सर
yeah.
दैट द जो मतलब सर मतलब फीलिंग नहीं आ पाती है ना इंग्लिश में इतनी, पर मैं
Okay,
कोशिश
okay.
करता हूँ।
So, as far as I know, I will tell. So this is kind of how it is. Like let's look at the side, okay, from this angle. So we will have if this is C, okay, this is C.
सर इस चीज के बारे में मेरे को पता है एबीसी एबीसी कैसे है, इस चीज के बारे में आई नो
Mm-hmm.
सर। आई वांट टू आस्क दैट सर, जो नीचे जो एट द बॉटम देयर आर फोर स्फीयर्स
Mm-hmm.
दैट कैन बी कंसीडर्ड एज ए, एंड द स्फीयर्स व्हिच आर एट द फेस ऑफ द क्यूब
Mm-hmm.
व्हिच कैन बी कंसीडर्ड, उनको बी मान सकते हैं।
Oh no no no. That because you see this diagram, no? Since they are like you know arranged in this sort of a plane, right?
Yes, sir.
Say I think 1 1 1 plane. So that is why if we have a look at this diagram, this corner we have C, whereas these two corners we have B, right?
सर मतलब मैं ऊपर आई एम नॉट सीइंग दिस डायग्राम फ्रॉम द वर्टेक्स पॉइंट ऑफ व्यू, आई
Okay.
एम सीइंग द डायग्राम फ्रॉम द प्लेनर पॉइंट ऑफ व्यू, फ्रॉम द बेस ऑफ द स्क्वायर।
Okay, okay, from the base. Ha 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 ha.
सर वहां से कंसीडर करते हैं तो एक जो नीचे लेयर है, दैट द स्फीयर्स आर एट द सेंटर, आर एट द कॉर्नर, बॉटम फेस ऑफ द
Ah,
क्यूब,
yeah.
स्फीयर आर एट द कॉर्नर।
Okay, yeah, yeah. At the corner we have one A, and actually we will be having a C at the bot. The cornermost will have a C actually.
नहीं
See?
सर, मतलब आप मेरी बात भी तो सुनिए सर। मतलब मैं ये जानना चाह रहा था कि अगर पूरे बेस को ए मान लेते हैं, if we consider the whole base as A,
Yeah, yeah.
the sphere at the face center as B, then the
Mm-hmm.
above layer of the cube as also A, as it is not different from the bottom layer.
Mm-hmm.
So yeah, this logic can be also fitted that it will be AB AB.
Ah, yeah. That will be
पर सर
because
वो
yeah,
AB,
everything becomes A, and then we have only P over here, no?
हाँ सर, पर सर इसको AB AB बोलते नहीं है, ये दिक्कत है।
Uh, Sorry, I didn't get you properly.
मतलब सर ये मतलब why this is not called as AB AB from that perspective?
No, no. Actually, the thing is, when it comes to these unit cells, right? Usually, this arrangement, it is actually like standard as in sometimes like you will have multiple phases also. Okay, so at that time we will be considering this as one element. Okay, even if we are considering same element also.
Excuse me, sir.
Yeah,
Please.
yeah, yeah.
The class is over, sir.
Yeah, yeah, that is the thing. Okay, I will.
May I leave now, sir?
Yeah, yeah. It's better we end it now. But
Yes, sir.
you can leave. Like whoever wants to leave, they can leave. So yeah, actually you are right about that. But I will just check like why it is considered strictly ABC. So your logic sounds correct to me, but I will anyhow I'll verify and I'll let you know, bro. Thank you.
Okay sir, thank you sir.
Yeah, sure. Thank you so much. Thank you. Yeah. Thank you, guys.